So far, we said that if you wanted to write a reasonable, a plausible Lewis structure, your best bet is usually to go with the octet rule. Now, there are exceptions, and the octet rule is in fact not a very strict rule. Okay, it doesn't have to be followed all the time. Now, there are some molecules, particularly with boron and involving boron and beryllium, that can be better represented by structures where the boron or the beryllium has less than an octet. So, for example, let's look at beryllium hydride. Be, if you look at the periodic table, is in column 2A, so it has two valence electrons. Each hydrogen has one valence electron, so there's two of them in BeH2, so that gives you four valence electrons. So if you surround your beryllium with two hydrogens, remember each hydrogen can only form a single bond, then you got your four electrons right there, nothing more to distribute, your four valence electrons, so your boron doesn't have an octet, your beryllium doesn't have an octet. There's just no way to go get more than four valence electrons around the beryllium in this case. Okay, what about BF3? BF3, boron, if you look at your periodic table, has three valence electrons. Each fluorine has seven valence electrons. There's three of them, so that gives you 21 plus 3, that gives you 24. So let's draw the Lewis structure for boron trifluoride, BF3. So let's surround our boron with three fluorine atoms. Remember, fluorine atoms are univalent, so they have to form a single bond, so they can only bond in this case to the boron. Okay. Well, let's see. We need to give octets to each fluorine. So, right, this fluorine on the left has one single bond, so three more pairs, so three lone pairs would give it an octet. The fluorine on the right has a single bond, so it needs three more lone pairs to give it an octet. The fluorine at the bottom here has one single bond, one pair, so three more pairs, three more lone pairs to give it an octet. And so far, what do we have here? You have 8 over here, an octet on the fluorine here, an octet on the fluorine here. So that gives you a total of 24. Okay, so the boron has only 6. 1, 2, 3 pairs. So that's only 6 valence electrons are on the boron. So that's one possible resonance structure for BF3. And in fact, that seems to be the best structure based on experimental observation. But you might say, it is possible to give boron an octet if we were to imagine moving one of these lone pairs into a bonding pair. So if you have boron with a double bond on the fluorine here, so the fluorine that's on the right will now have just two lone pairs left, and then the boron, the other, and then you have the other fluorines still with three lone pairs. Okay. Now you can see that your boron has an octet, 2, 4, 6, 8. Okay, so that looks like everyone's happy now. Every atom here has got an octet, but let's take a look at the formal charges. Formal charge on the boron. Okay, by itself, a free boron atom would have 3 valence electrons. It appears to own how much here? I have 4 bonding pairs, so half of 4 bonding pairs is 4 singles, no lone pairs. So it appears to own 4 electrons in this structure. So 3 minus 4, that gives you a -1 formal charge on the boron. And on the fluorine, okay, the fluorines over here would have 0 formal charge. This one down here is going to have 0. The one on the right has, okay, a free fluorine atom would have 7 valence electrons. The fluorine here that's doubly bonded, the one on the right has 2, 4 valence electrons from the lone pairs, plus half of the 2 pairs, that's 2. 4 plus 2, that gives you 6, right? So 7 minus 6 is +1. So the fluorine here is a +1 formal charge. Okay? Now, the experimental observation suggests that this particular resonance structure of BF3 is actually less significant compared to the other one. And so it would suggest that one possible explanation we might say is because here you are giving your boron a negative formal charge. So, and then your fluorine, which is the most electronegative atom, ends up having a positive formal charge. So that doesn't look good for boron and fluorine there. Whereas if you go back over here, all the atoms have zero formal charge on the boron and the fluorine. So it appears you have a competition here between the octet, getting an octet and getting all zero formal charges, and it appears in this particular case, experimental data suggests that the formal charge argument, the formal charge seems to win out. Having a zero formal charge seems to be a better deal. Okay?